The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thank you for joining us today for our webinar with our speakers, John Bull and John Sanders with Carus. I'm Ashley Swingle, Marketing Specialist, also with Carus. A few housekeeping items before we get started. All attendees are in listen-only mode to help cut down on any background noise. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through GoToWebinar, we will receive a report with the question and your contact information to follow up directly after the webinar. If you're interested in receiving a PDF or recording of the presentation, please contact us. We encourage you to share the recording within your network. Here are a few ways to find us. We have listed our website and general sales and marketing email address, as well as my email address. You receive our email blasts for upcoming webinars, presentations, trade shows, and technical information on our various solutions. If not, sign up on our website. You can find the Join Our Email list on any landing page on the right-hand side. Be sure to select the industry when signing up to ensure you receive the most targeted information for your needs. And don't forget, we have social media platforms. We encourage you to connect with our Carus page as well as our team members on LinkedIn, where we are often sharing upcoming events, including webinars, industry articles or news, sharing relevant posts from other industry experts, and more. Listed here is our website and our link to our webinars. At this time, I would like to take the opportunity to introduce our speakers, Mr. John Bull and Mr. John Sanders. John Bull is the Global Technical Program Manager for Carus. He has been with Carus for over 45 years, serving in a variety of sales and marketing positions. John earned his BA in engineering from Purdue University. He's a member of the Water Environment Federation and the American Waterworks Association, where he served as the AWWA Illinois Section Chair from 1992 to 1993. John Sanders is the Regional Sales Manager of the Gulf region for Carus. He graduated from Trinity University in San Antonio, Texas, with a Bachelor of Science degree in both biology and chemistry. He's a member of the American Waterworks Association, American Chemistry Council, and the American Society of Sugarcane Technologists.
Thanks, Ashley, for getting us started this morning, and welcome to everybody to our presentation on permanganate products and how they're used in the oil and gas industry. And welcome to John Sanders. I'm glad to have him on as a co-presenter today. Well, my plan is to follow a very basic outline with some background information on permanganate chemistry and permanganate products, a little bit about oxidation chemistry, and then I'll introduce the various uses of permanganate in refineries and in oil field water treatment. So I'd like to start with some background on permanganate, and really in chemistry terms it falls into two descriptive buckets. In the one form, it is a transition metal, manganese, and it's really very similar to iron. It's present in the Earth's crust, and it's an essential micronutrient for life. In the second bucket, permanganate is really an oxidizing agent. It's an important group of reactive compounds, and that are one half of the practical oxidation-reduction reactions that take place every day. So permanganate is a transition metal found in the first row of transition metals on the periodic table right next to iron. Manganese is an essential nutrient for plant and animal life, and it has several large-scale commercial uses, such as the manufacturing of steel and the use as cathodic material in rechargeable batteries. As a transition metal, manganese can take on a variety of different chemical states simply by swapping electrons. And I often, at this point, like to mention that manganese is sometimes confused with magnesium, which is in the second column. Both are found in water supplies, but they're quite different in their properties. So what is an oxidizing agent? I think if you're not familiar with oxidation, or your customers are not familiar with oxidation chemistry, it may be helpful to just think of it as a form of energized oxygen. Now, to the chemists, of course, it's all about accepting electrons in oxidation and reduction reactions. It's quite likely that the name oxidation is a result of observations of our physical world. We live in, after all, an atmosphere of oxygen. And it was soon noted that almost all elements form oxide compounds just by being exposed to the air. Now, when heat and light are evolved, this rapid oxidation is often referred to as combustion. Note the reactions that are shown here, and keep in mind the slow rusting of iron producing reddish-brown iron oxides. There is an analogous reaction in water treatment that we'll talk about in a little bit. There are many commercial oxidizing agents available in the marketplace, including oxygen in the air, energized oxygen in the form of ozone or peroxide, chlorine compounds, ferrates, which are iron-based oxidants, and advanced oxidation processes, AOPs, they're slightly different because they release hydroxyl free radicals. But all of these oxidizing agents are quite different in their physical forms, in their stabilities, and in their speed and degree of reactivity with various pollutants. Permanganate products are also available in different physical forms and compositions. As a crystal and powder, permanganate is very concentrated, but it has a very low water solubility. Permanganate can be modified to increase its water solubility up to 40% by weight. And in a convenient way, it is a convenient way to really feed and receive permanganate products. Permanganate can also be blended with other synergistic components that will increase the speed of reaction or improve its efficiency. I've listed two blended products here on this slide, Carus Plus and Totalox Odor Eliminator, because both of these have found uses in the oil and gas fields. I mentioned that permanganate's a stable compound under normal conditions, so it can be manufactured at one location, such as our plant in northern Illinois. It can be packaged and delivered to a site where it will be used. The manufacturing process starts with manganese dioxide ore, which is plentiful in the Earth's crust, and we apply oxygen, heat, and energy to that ore to raise the manganese oxidation potential from +4 to +7. That's permanganate. When the customer uses permanganate, they're simply reversing this process, taking the energy back out for some important purification step, and manganese dioxide remains in the end. Now, whether you're using potassium permanganate or sodium permanganate, the active ingredient is the same. It's the permanganate ion, MnO4-1. But there's one major difference between the two, and that's their solubility in water. If you compare the solubility curves at 25 degrees centigrade, you see that sodium permanganate solubility is about 10 times higher than that of potassium permanganate. If you've worked with permanganate before, you know that in water, it has a distinctive purple to pink color. And in this photo, the color change is apparent in the low parts per million concentrations. The depth of color is directly related to its concentration, and this correlation is linear. This means that we can measure permanganate concentration by simply measuring the color in terms of light absorbance on a spectrophotometer. And I'll finish this section on permanganate chemistry by just addressing pH conditions. Permanganate reactions can be influenced by pH, although in most practical environmental applications, the pH range of 3 to 12 is what is common. In this range, permanganate undergoes a 3-electron transfer, and manganese oxide precipitates as an insoluble hydrous flock. In the extreme pH ranges, they are sometimes used in specialty applications, but the end products in those cases will be completely different. Okay, so let's talk a little bit about permanganate applications in refineries and in oil fields. There's really a long history now of permanganate use in oil and gas processing and in petroleum refining. Permanganate oxidation chemistry is especially effective for certain common impurities and pollutants that are found in oil and gas processing and refining. In particular, the destruction of hydrogen sulfide and organic sulfur compounds are very important, and also the neutralization of pyrophoric iron sulfide. Permanganate is known to react rapidly with many odorous organic and inorganic compounds, and permanganate's speed of reaction is really what makes it an effective treatment. Often these applications are specific to wastewater streams or accumulated sludges in tanks or in ponds and lagoons. The oxidation destruction of phenol is another example of wastewater treatment. And we can't forget about controlling hydrogen sulfide, which in the oil and gas industry is an extremely important safety concern due to its adverse health effects. Now let's talk a little bit about permanganate uses that are specific to refineries, and let's start with equipment surface cleaning. The cleaning and descaling of carbon steel and special alloys uses alkaline permanganate solutions, and this was pioneered by Carus technicians over 50 years ago. The chemistry has been adapted to many industries, including petroleum refining. In this case, the use is really about equipment cleaning. Heat exchanger tubes that have become clogged or blocked with organic scale are flushed with hot permanganate solution to restore them to clean condition. Companies that specialize in scale removal and boiler treatment are the true experts in this application. But this idea of cleaning the inner surface of metal equipment has also been adapted to refinery process equipment, where the buildup of pyrophoric iron sulfide creates a safety hazard when it is exposed to air. Because of the widespread production of pyrophoric iron sulfide, permanganate has been used in a variety of different processes. The process unit cleaning and tank cleaning listed at the top here really refer to the pyrophoric iron removal from equipment, and sulfide oxidation when the tanks are dewatered. We'll talk a little bit later about the produced water treatment applications of permanganate. And of course, always remember that industrial sites have a lot of wastewater issues that can be handled by oxidation. So what is pyrophoric iron sulfide? Pyrophoric iron sulfide is really formed when the sulfur in hydrocarbon streams comes in contact with any source of iron, and it can be formed in a variety of different process units. During normal operations, pyrophoric iron does not cause a problem. However, when the unit is opened for inspection and maintenance, the pyrophoric iron will dry out, and it can auto-ignite when it is exposed to air. To eliminate this hazard, permanganate solutions are recirculated through the equipment to oxidize the iron sulfide scale. And a surfactant wash is generally used first before the permanganate treatment in order to remove any hydrocarbons that might coat the pyrophoric iron. After this permanganate treatment, the unit can be opened up and exposed to the air with no hazardous conditions. I mentioned that hydrogen sulfide is another contaminant or pollutant that you can find in refineries and in oil and gas fields. And the control of hydrogen sulfide can be accomplished in a variety of different ways, but to destroy it, you really must use an oxidizing agent. So why select permanganate? Well, permanganate is often selected because it's very effective and very fast. In this graph shows that the permanganate reaction with H2S is immediate, making treatment time short. Also, the chemical addition point can be near the point of H2S release. There's no need to inject permanganate far upstream of that point source of hydrogen sulfide. Phenol is a common and highly regulated wastewater pollutant that is used by many industries, but refineries are impacted because phenols are a common component in crude oil. Permanganate reacts quickly with phenol to alter its structure in a reaction that fragments the phenol ring, and this eliminates its toxicity and improves its bioassimilation. When discharged to a wastewater treatment plant where a secondary biological treatment process is being used and where it's normally acclimated to phenol, it will be removed by that bacterial process. But when unexpectedly high concentrations of phenol are rapidly discharged to the plant, it can be toxic to the bacteria and it will upset the biological process. Pre-oxidation with permanganate will fragment the phenol molecule into smaller organic acids that are easy for the treatment bacteria to assimilate. Very low levels can be achieved with permanganate, and I should note that these reactions are not instantaneous, however. Reaction times are minimally about 20 minutes. So in the case of phenol destruction, permanganate oxidation treatment will help you meet very low discharge standards. It can be effective over a broad pH range, although alkaline treatment is certainly preferred if it can be achieved. There are fast reaction times that range from about 20 minutes to maybe 1 hour, and it is very cost competitive against other oxidizing agents. Now I'm going to move upstream from the refineries to the oil fields and introduce the work that we've been pursuing in that area and in the area of produced water treatment. First, I've included on this slide a little bit about to define what produced water is and to provide a little bit of background on produced water. Notice that produced water may contain many natural contaminants, and you will see that these contaminants include dissolved iron and dissolved sulfides. These are two contaminants that permanganate efficiently oxidizes and removes from water. And John Sanders has been conducting many field tests in West Texas. So as I mentioned, it's great to have him here, and he'll walk us through some of his findings in just a little bit. And I was surprised in researching for this webinar today that the references to permanganate and produced water treatment go very far back. There is a reference I found that dates back to 1949 that describes the benefits of treating oil field water with potassium permanganate so that that water can be recycled back to the formation. And here's a quote from East Texas. The treatment of oil field produced water with permanganate removes the dissolved sulfide and thus improve the viscosity and performance of the polyacrylamide polymer. I was really surprised that we could find a reference that goes that far back. Now, here's a simplified diagram of produced water flows in the field. And you can see on this slide from the well formation and well production, and the well production could be a conventional well or a non-conventional well. The oil and water are first separated, and this all takes place very near to the well itself. And then after the oil is separated, you have produced water, and it may go through very basic treatment, and then it can be typically disposed of by deep well injection. It's referred to as saltwater disposal. But now the need for produced water is becoming greater, especially in areas, as you can imagine, where water is scarce. So by doing some advanced treatment of this water, you can produce water that can be recycled back in and used in the formation. And in advanced treatment, what they're really referring to here is some oxidation treatment, such as with permanganate, and then coagulation and flocculation of the solids that precipitate out after the oxidation reaction, and then clarification and filtration to remove those solids. Now, there is also discussion about doing further treatment of produced water so that it can be used in other end uses, such as agricultural, irrigation, and surface water discharge, and other high-end types of water applications. So why is permanganate being used to treat produced water? Well, typically, it has to do with one of these 5 application treatment processes. First, iron is removed by oxidizing soluble iron 2 to insoluble iron oxide or iron hydroxide. That floc is then removed by clarification or filtration. Or the permanganate may be applied to remove the sulfide that is present and dissolved in the water. This can also include other reduced sulfur compounds as well. The sulfur compounds are controlled by oxidation conversion to higher sulfur oxides and possibly to sulfate as an end product. Thirdly, the addition of permanganate increases the oxidation-reduction potential, which we also use as an indicator of that we're using or applying the correct permanganate dose. We are also using and taking advantage of the manganese dioxide floc that forms, especially manganese oxide floc that forms in conjunction with iron oxide floc, where they can act as a coagulant aid. And then these flocs can also remove other impurities by absorbing them on to the floc surface. Now, one of the hurdles to actually treating produced water is that the quality of the water that you're going to be treating varies quite widely from site to site, even from well to well. And in addition to that, the standards of how clean the water must be are not quite consistent either from location to location. But you can see here are some suggested standards that might have to be met for a lot of the water quality issues in produced water, and in particular, those that permanganate may help to treat. And you can see that the sulfides, they would quite likely like them to be 0. Iron can be only as much as 25 or sometimes lower to 10 milligrams per liter. And then you're always trying to remove that last bit of residual oil and any other suspended solids. I'm going to include here just very quickly very common inorganic oxidations with permanganate. And they include the oxidation of soluble iron and the precipitation of iron 3, the oxidation of arsenic to arsenic 5, and then arsenic 5 can be absorbed onto the manganese dioxide that we're producing. We have a rapid oxidation with reduced sulfur compounds such as hydrogen sulfide. And then the last reaction I included is that reaction in neutralization of pyrophoric iron sulfide, which I mentioned during refinery turnarounds and tank cleanings. One of the important reasons for listing these is I wanted you to go away with the thought that these reactions are very fast. So sulfite reactions in seconds, nitrites, iron, arsenic-3, very fast within seconds. And then sulfides in particular, a little bit longer, but certainly complete within 4 or 5 minutes. And that's important because here is a typical treatment program that is being used in the oil fields today. You can see that speed of reaction is important because there's often very little opportunity to separate the injection points for all the treatment chemicals that they're using, especially prior to solids removal in coagulation and solid separation. Permanganate should be added to the produced water before the coagulants so that the oxidation reaction can go to completion and the solids can be effectively dropped out. Now I'm going to call on John Sanders to join us because he's going to talk a little bit about his field and laboratory trials. And I would just say by way of introduction that permanganate chemistry can be easily tested in the laboratory or in the field by just preparing a stock solution. Usually it's a 10 gram per liter solution. And this can be dosed into samples of produced water and tests and observations run on those samples. So John, I'll let you take it over and let me know when you want me to change the slide for you.
All right, thank you, John. Go back to the previous for a second. All right, the picture on the right, and like John described, I'm going to go through some field and lab testing that we've done out in the West Texas area on actual produced water treatment sites. Generally, the first test that we conduct is a permanganate demand test. We'll go out to the site or get a sample of raw produced water that's incoming, and we will dose it with differing dosages of our permanganate products and look and find out what that demand is. So as you can see, we've got 20 parts per million all the way up to 120 parts per million. Typically invert that sample, get a little mixing, and then draw out and syringe filter a sample out of the bottle and look for a color change. If we see pink or purple after the filtration process, then we generally assume that we are overdosing on that dosage. If we get it down and it's clear, then that kind of gives us an idea of what our target dosage is. But it's a good way for us to get some basic information on what we're looking at for the overall demand before we get into the other testing and adding other coagulants or polymers and doing more extensive testing. It gives us that target dose, which will give us an idea of where to go from there. And like John said, typically it's easiest just with starting with a 1% stock solution, potassium permanganate, and we can easily extrapolate that into our other products if we need to for dosage. Next slide. This next one looks simply at iron removal treatment application. This is from a produced water treatment site, and you can see on the left the data of the iron going through the various stages of treatment. The incoming raw was around 50 milligrams per liter. At that point, our potassium permanganate solution was injected very early in the process prior to any coagulation or flocculation. And you can see it through the process that it was knocked down to post-clarification, 1 milligram per liter. Then there was a filtration step, 1 milligram per liter, up to the pit entrance, and then on to recycled water, which would be stored and sent back to be reused again in the fracking operation. So Permanganate did an excellent job and very rapid through the first step of removing that iron. And you can see the various jars taken from the different stages of treatment and the clarity of the water as we go through the treatment process. Next. One of the variables that is very important to the operationers and the end users out in the produced water treatment is maintaining and achieving a good oxidation reduction potential. And permanganate being a strong oxidant, when you use it, you increase this oxidation reduction potential, or ORP, and it's a good indicator if we're at the correct dosage or not. If we do a dosage and we're not achieving that ORP, then we keep increasing it till we get to that standard that's expected on the KPIs out in the field. The graph here, we have ORP on the left, and then we have the dosages of two different products. One's typically just potassium permanganate at 40 milligrams per liter. The other is a blend at 40 milligrams per liter. This particular blend is a permanganate, sodium permanganate, and a sodium hypochlorite blend. So you can see the ORP for the raw, typically very low, oftentimes negative. And with the addition of the permanganate, we were able to get it up to 500 millivolts, which is a very good, oftentimes higher than it's even required out there in the field. So they were both products were very successful at increasing the ORP number. Next. This next set, we look at some oxidant comparisons, both on ORP achievement and iron removal. And the oxidants that we used were the blended product again, regular standard potassium permanganate solution, and then also peroxide. And this was done at a site where they were using peroxide, so we wanted to look at these different variables, and we tested permanganate against it just to see what type of number we were achieving. The left graph is the ORP comparison. Again, the furthest column is the raw water, which is at a negative 63. And then we can see permanganate and the blend were at a dosage of 20 milligrams per liter, whereas peroxide was at 80 milligrams per liter. And you can see all three were very similar on the ORP number. The blend of the sodium hypochlorite, sodium permanganate was very successful and actually achieved the highest ORP value at a much less dosage than we see with the peroxide when we looked at the comparison. And then on the right, we looked at the iron removal, same dosages for all three products. We see the tall blue column is the raw iron up in the kind of the mid 30 milligrams per liter. And then we can see again, the blend, the permanganate solution, and then the peroxide, all generally were 2 ppm or less. They all three, met the KPIs for this typical location, but it showed that not only the ORP was met, as well as the iron removal was met by all three products, but the permanganate products at a much lower dosage. Next. This is a little complicated, so we'll walk through it, but what these two graphs on the slide are trying to show is on the left one, ORP reading, we're comparing our standard permanganate 1% solution with our permanganate blend product. And then the right graph is comparing the same ones, same dosage with iron removal. And what you can see is the blend, we were able to achieve a high ORP reading at a much lower dosage, down between 20 and 30 milligrams per liter. And on the permanganate 1% solution, we had to go up to 80, 90 ppm milligrams per liter to achieve the same ORP. And then looking at the right, same thing. We got the oxidant dosage of the blend, and we removed almost 45 milligrams per liter of iron. We dropped it down to 1 milligram per liter or less, very low. The target was 2. And then the same, it took much higher, up to almost 60 milligrams per liter of the potassium permanganate solution. So the blended product showed some of these capabilities to use less product, and we were still able to achieve good ORP numbers and good iron removal numbers as well. Next. Another factor that's important that we looked at is ATP treatment results as well. And one thing I need to preface is permanganate products are not registered as a pesticide under Federal Insecticide, Fungicide, or Rodenticide Act administered by the US EPA or similar state laws. So get that out. But we did look at some testing results. This particular one is from a saltwater disposal. The far left is the raw ATP concentration, very high. And then we looked at varying dosages of the permanganate solution, 5 milligrams per liter all the way to 150 milligrams per liter. And then we can see as we increased our dosage, we were able to achieve more ATP lowering. Next. All right, John had mentioned earlier that one of the results of the permanganate reaction is that we have manganese dioxide released, and it's a solid. It has good surface area, and it also has a slight charge to it. So it works very well as a coagulant aid, also kind of a seed material. So it's interactive with inorganic coagulants and also polymers. So it helps attract and absorb impurities, which will help with overall removal and clarification. And some of the things we've seen out in the field and in jar testing is that we get this improvement to an extent that we can even use less of the inorganic coagulant or remove it altogether because the coagulation effect of the MnO2 is very effective, and it works synergistically with the polymer to the point that we're able to capture some of those savings and have reduction or removal of an entire product on the coagulation side. It's also very effective to provide an active surface for the oxidation of sulfides by dissolved oxygen. Next slide. And the next slide is just kind of showing this in a real world scenario. This is some jar testing again that was completed on produced water. The first picture is the raw produced water. The middle picture shows 25 parts per million. This is of a 1% potassium permanganate solution added. And what you can see is the flocculation that occurs. That's the reaction. That's your MnO2 solid coming out. So it provides that seed material. When I inject the polymer, we get very good flocculation. We get very good solids dropping and very good clarity on the end result of the water. So this just kind of shows step by step how the manganese dioxide is helpful in the coagulation and clarification process. Next slide. And the next one is just using flowback water, which is much more dirty, much more contaminants in it than standard traditional produced water, and requires a higher dosage. But again, we see the same effect. We inject 80 parts per million of the potassium permanganate solution, which starts to seed. We get the flock out of the manganese dioxide, and then when we add the polymer, we get a very, very good reaction and dropout. And again, there's no inorganic coagulant being added. It's just the potassium permanganate solution followed by a flocculation polymer. So we eliminated a step, and we got very good clarity, very good solids generation, very good flock, and as you can see, you know, clear supernatant on the top and a very good flock dropped out on the bottom. Next. This next one is kind of a full treatment process jar testing. Again, this is from active site, and this site again was using peroxide as its chief oxidant. They were also using polyaluminum chloride, using some caustic soda for pH adjustment, and then they were using a polymer, flocculation polymer at the end. And what we did is we did a comparison. We added our permanganate blend, which is the sodium permanganate, sodium hypochlorite, at a dosage of 20 milligrams per liter. And these are kind of the results that we got. And there's all your water on the raw, the pH, the negative ORP, the total, the iron that's in there. And then here's what we get after treated. So our pH 7.1, we've got the ORP up to 270 millivolts. We got the iron down just above a part. And at this site, it had a parameter of less than 10. So very good. And the turbidity was 8.5 NTU on the supernatant, which is very good. This had a very loose site of 100 NTU, but other sites we've seen much less than that. So these were good initial jar testing results. We see again very good flocculation in the jar. You can see in the picture. Next. All right, this last one I'm gonna let John go through. It was a project that we were both present for out in Midland with some testing, and I'll let him go through this process.
All right, thanks, John. John mentioned that the manganese oxide, especially freshly precipitated manganese oxide, acts as a very nice oxygen transfer catalyst. This was a reaction that we really investigated back a number of years ago because of high sulfide levels in refinery wastewater and also in spent caustic material as well. And we wanted to see if what the literature told us about oxygen transfer with manganese oxide could really be duplicated in the field. It's a little bit of a tricky slide, but you can see the blue line across the top is sulfide removal using just oxygen, just by aeration alone. And it does remove some sulfide. It certainly could remove sulfide by stripping it out of the water, but it is a slow process. And then we compared that to using potassium permanganate, but at a very much lower concentration than what the stoichiometry of the reaction would tell us we needed to use. So only a small amount of permanganate by itself. And of course, once all of the permanganate is consumed, then the sulfide removal really stops after that point. So we look then at what happens if we were to use a manganese salt instead of potassium permanganate as a raw material. And we used manganese sulfate, and we combined that with oxygen aeration. And sure enough, it removes the sulfides as well. This wasn't a new idea. The tannery industry, which had very high sulfide levels when they would process hides, investigated and used this manganese sulfate oxygen combination many years ago, although it does have to be done at a higher pH range. And then finally, we wanted to compare using potassium permanganate, where the permanganate will react initially, produce freshly precipitated manganese dioxide, and then we will combine that with air. And you can see that the removal is really quite good under these conditions, and the reaction rate is very, very fast. And John and I actually applied this at a site in West Texas where the sulfide loading was quite high, and they were looking at aeration being provided by a company out of California. And we said, well, why don't you try adding permanganate and the aeration together? And it worked out really, really well. The sulfide levels were reduced pretty dramatically. And it really is a good process of combining permanganates, manganese dioxide, and air to react with very strong reducing agents such as hydrogen sulfide. So that is our webinar for today. Let me summarize very quickly that permanganate is a stable oxidizing agent used a lot in water and wastewater treatment. It's commercially available as potassium permanganate, a crystalline solid, or as sodium permanganate, a pre-dissolved concentrated liquid. Permanganate is a safe chemical oxidant to use, which is why it is accepted and used at refineries. Permanganate is effective for controlling pyrophoric iron sulfide, mercaptans and thiols, hydrogen sulfide, phenols, amines, and other refinery contaminants. Permanganate provides energized oxygen for useful water purification processes such as iron and sulfide removal. So it can be added to produced water as the first chemical treatment ahead of clarification and filtration to remove that iron and sulfide contamination. And the manganese oxide helps to improve water clarity as well. So now I'm going to turn it back over to Ashley, and you can finish up for us.
Okay, thank you both. That was great information. Our current slide here shows our sales managers along with their contact info. And then if you want to go to the next slide, John. Thank you. Okay, this slide here shows both of our presenters' information, email, phone number, as well as our website and sales and marketing email address. So if you do have any questions, feel free to submit those. Otherwise, I think that's it. Thank you for tuning in, and thank you to our presenters. Have a great day.